Yes, I want this to be as much as possible. Or be as possible you can mute and answer. So, um, um, what would you say? What would be your answer? Hello?
So I want by say they are chemical engineers,
Okay.
but my hunch is saying maybe mathematicians. But I'm going
Mathematicians.
to say chemical engineers because engineer.
Okay. Anyone else? Anyone else? Okay, yeah, so you're right. It's actually chemical engineers. But then for me, what was surprising was learning to see how long this thing has been around for. So it came on the scene in the 1970s, and it didn't come from academia, it actually came from industry. So this idea of model predictive control had been out there, but then up until the 1970s, no one had actually put together as we see it today. So having all the flavors, so having to make future predictions, having to optimize future behavior, having to systematically handle process constraints. These guys were the first people to really do it like that. So there's been other types of advanced controls where they make use of an explicit process model or make future predictions. But then to have all these things that I mentioned here, it was first done in the 1970s by two different groups. So there's one called ADESA, and then the other one is Shell. So this IDCOM is just identification and command, and DMC is dynamic matrix control or controller. So then the question comes up, why model predictive control, right? So the first and foremost is that markets, as we see today, are very competitive. There's so much uncertainty. And when you look at environmental uh, requirements and safety, you see that these are getting stricter and stricter, which meant that to really stay on top of your game as an industry, you have to be smart about how you operate. You have to really push towards the bounds. You have to do the best. You have to really push your process. So an outcome of this is that control needs got specialized. So historically, you design a plant, you calculate a single operating point, and then you hope to operate at that operating point. If you miss it slightly, you don't really care. But then when you're in the market where margins are tight, you have a lot of people to compete against with. You have to make sure you do things really well. So there was a need to find much more sophisticated needs of controlling the plant to operate at the burst point. I'll say at the burst point later on. I'll change my terminology, but for now, I'll say the burst point. And this can be quite complex to find. So finding an algorithm that is able to take this thing head on was really key. And as I mentioned earlier, having to handle constraints was really big. So when we talk about constraints, we simply mean that there are limits that you have to respect. For instance, you are not going to buy fuel that has some kind of impurities, let's say has some amount of lead, right? So the fuel that you buy at the pump needs to meet some form of threshold, and that you will call the constraint. Um, you cannot pollute too much. You cannot release too much flue gas when you're operating your process. So the limits for that release of not so clean gases. You have to respect that. So these are some examples of constraints. Then, of course, there are process and nonlinearities. So, for instance, you take a reactor. So you don't, and when you look at the relationship between, say, the rate of reaction and the concentration, you don't have, would I say, a linear relationship. So the relationship is sort of like cubed or squared. So things like this you call nonlinearities. And then of course there's model uncertainty. So model uncertainty says that you don't have everything uh, exactly. So you compute and then you compare to the process. There's a bit of a difference. And of course, you have you want to be able to be exact in how you define your goal, right? You don't want to just say, okay, I want to do something, but you want to say, hey, I want you to operate at this point, right? So putting all of these together, there was a need to come up with a control algorithm that will be able to address all these. And these are the main motivators for model predictive control and why it has been successful. So speaking about it being successful, you want to see the extent to which it's been received by industry. So as I mentioned earlier, this is not a technology that came from research groups. This is not a technology that came from a university somewhere, sorry, but rather industry. So this is a survey showing the level of penetration, and this was done in 1999. So you can imagine uh, 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 what the penetration would be today. So as at that time, and for the people who responded, there were more than 4,000 industries that were already using model predictive control from many vendors. So you have the segments of the industry here. So refining, petrochemicals, chemicals, pulp and paper, air and gas, utility. And the examples of the technology providers are Aspen Tech. I'm sure some of you are familiar with Aspen Tech. For those of you who got the chance to do internship in industry, I'm sure you've come across things like DCS/SCADA, and a number of these things are actually supplied by Honeywell, and there's one of the first people to actually develop the MPC algorithm. You have investors, and you can see the numbers with respect to the penetration. So not too surprisingly, petrochemicals and refining are on top because they were the first people to kind of develop it. So as of 1999, which if I'm to take a guess, a lot of you were not born. There were so many people already using it. So today, it's even reached much beyond these numbers here. So next, I talk about the place of MPC. So when you think about MPC doesn't act in isolation. Now, before I continue, is it possible to get a poll of the years that you guys are in, say maybe first year, second year, third year, and fourth year?
Alan,
Hello?
is that possible? Can you run a small poll whilst this thing is happening?
Yes, please, I can do it.
Okay. Or maybe randomly people should just type in the comment section what your year is.
I can do that.
I'll do some. Guys, can you just type your year?
Yeah, so it doesn't have to be exact. I just want to get a sense so that I can tailor my message, because I run the risk of either going too deep or being too much on the surface. But Jude, if you had to guess, what would you say most of the participants are coming from in terms of their
Coming
year?
from? So give or take, most of them will be in third and final year.
Okay.
There are even some postgrad students in the, I least I've seen a PhD student and some, I think, 2, 3 master students.
I see.
But yeah, there will be some. Yeah, so mostly, yeah.
Okay. So
Yeah,
so
teaching
the next
assistants.
question is sorry. So the next question is how many of them are familiar with not familiar. I mean, I'm sure a lot of us are familiar with process control, but have a decent understanding of process control or some familiar.
So when it comes to the final years, I think
Yes.
in the first semester they do what they call process control instrumentation.
Okay.
So not the maths,
Okay.
but like this equipment does that, this equipment does that, that equipment does that. They do that. Use this thermocouple for that, some
I
stuff
see.
like that. Then
Okay.
the second semester, that's when they do the modeling. So it's
I
only the
see.
graduates will have a good understanding. The final years they have some understanding.
Okay. Okay, that's good. Okay. So good. So my guess is that for final years you've probably looked at sorry, before I move on, thank you for your answer, Jude. So if I'm to guess, the final years have already learned about things like PID controls, right? Or
PID is much more second semester
okay.
vibe.
Oh, the
Oh,
calendars.
guys, speak for yourself. Okay, someone said yes. Ish.
Okay.
It is like
Okay.
I'm not the one teaching it here. So they know that
Okay.
you are proportional. Okay. They said
Okay.
yes.
Okay. Okay. That's good. That's good. So in PID, I'm sure for PID control, you work with what is called the set point or the operating point. And often you assume that you know that already. And then the question is where's that coming from? Right. And one of the places that could come from is just the design, right? So you design your tank in such a way that the flow rate out to the tank is a certain number, right? So that is one of them. However, in this era of market uncertainty, competitive markets, there's a likelihood that you're not going to be operating at that design point, right? And you need to kind of adapt your operations to kind of suit the market. For instance, so I don't know how many of you have done internships, but then if let's say you were to go to a place like Accra, that's where I did my internship. And this was an actual experience for me. Getting to the Christmas period, they have to ramp up operations. Question is, how do they know the extent to ramp up to, right? And to ramp up operations, you need to, find out how much material you need to kind of get to that target point. All this is just to show that your operating point slash set point is likely to change because you want to get the most out of your process, right? So at the very top, right, where you're tracking, output in terms of the number of plays that you produce, you kind of have to find a way of finding that. And one of the best tools for using to find that is optimization. So that's at the very top. So you're looking at the entire plant, right? So you're looking at raw material, you're looking at, utilities, you're looking at your output, you're trying to do the best. So with optimization, and I don't know how many of you have taken the optimization course. And it's okay if you haven't taken it, because myself, I took a different elective when I was at tech, but then I'll quickly just go through what optimization does. So optimization is a systematic approach for finding the best solution, right? So of course, it's a math formulation. You write it up, you give it the goal slash objective and say, hey, with this goal and this set of conditions, find me the best answer, right? So you're able to do that high level optimization. And then the answer that you get would be in terms of things like operating points. So you kind of send it down, right? And there are ways of handling this, right? As you send it down to the equipment, there are ways of handling this. So in the past, they had what is called heuristics for managing how information is sent down to the last unit where you kind of have your BNID controls. right? So as I mentioned, this is heuristic, this is not systematic. So what MPC did is to displace these heuristics between the high level optimization and the low level. Oh, okay. Thanks for that. Oof. I see. Okay, this is good to get this in. So I'm just seeing the poll. So yeah. Anyway, so you have the MPC displacing the heuristics approach, because yeah, and heuristics is a collection of sets of rules that you've determined over the years, but you are not sure that you are doing the best. However, with optimization under set conditions, you are guaranteed to some extent that that's the best you can do under the set of conditions. Already we do optimization at the very top. So if we can even do it at the much lower level, then we're able to take advantage of the resources at our disposal. And MPC even helps this get lower, right? So when you look at what is called the process control hierarchy / automation, this is what it looks like. So you have decisions that are over a longer period. So if you recall, I mentioned that you're trying to produce beer to meet demand for the Christmas period, right? And if you look at the Christmas period, you're talking about weeks. So your decisions may have to be done over days, right? And those decisions have to sort of like trickle down all the way to what is done in real time, right? So when you look at the automation from that high level all the way down, you have what we call the process of the automation hierarchy, right? So we see that model predictive control is not the silver bullet that came into the picture to come and clear everything. Rather, it came to just fitting, right? So it is complementary with other process control, would I say, approaches, right? So it was important for me to kind of establish that before I moved on to into what is in the model predictive control, right? So earlier on, I mentioned some features of model predictive control. The first one was that there was a need to have a model. And by model, you're talking about your set of equations that describe, say, your CSTL. That could be a model, or it could be your tank, right? So, and the tank could be simple material and energy balance, right? So you're looking at the amount of liquid coming in. If, let's say, something else happens in the tank, say maybe there's some kind of heat exchange, then of course you can include your energy balance. But first off, you need your explicit model. You need to have a way of simulating this model. So meaning that your model cannot be static, it has to be dynamic, right? Because you're trying to, sorry? Hello?
Oh, sorry, I think it was some disturbance on my end.
Okay. How are we doing in terms of time? Okay, good. Yes. So you have your model, of course, and of course that has you have your
King Charlie,
process,
what's up?
obviously. But then
I
your
talk this
process,
guy say make you do
you don't have all the information.
a
For instance,
co-host, right?
when
Yeah.
describing your
Yeah, so
CSTL, you
the guy
have
make
things
him the main
like
hoster, and then I'll go do you the
concentration,
co-host.
right?
So say
Most
in
of the
case
time,
of
you're not
any
going to
network
be measuring
issues or
all concentrations.
any on and off
So
things,
what that
yeah, then
means is
you go
that
handle
whereas
things.
your
Right?
model
Already I can't reach house. My
can
phone
give
do
you the
1%,
concentration
we
for
then
all your
offline.
components,
They're
when you
offline,
have your
so I don't
actual
know if
process, you have
it will be
limited
possible for me
information,
to join the meeting.
right?
But I'm just praying
And
that
that is
they are
what you
going
have
to
to
like
use
turn it on
in your decision making,
before
right? The model already helps you to kind
7,
of
right? Yeah, so say I go feed charge them, then
compute,
I'll go
and
did
that
the
would
inside.
then be used for your calculations, right? So you have your model, you're able to do predictions into the future, and you are able to compute inputs. Inputs are simply your leverages that you use to move the process. So if I'm to give an example, I can think of, say, your CSTR again. So maybe you're able to control the temperature off. the feed stream, that's an input, right? And what the MPC is trying to do is trying to help you determine the best flow rate to give the process under the set circumstances. So in terms of arrangement, this is what it roughly looks like. So the MPC would be responsible for the control calculations. The separate calculations will be coming from above, depending on what external conditions are, right? And that may change from time to time. And I have an example that I think would make this clearer, but this is sort of just to give you a view as to how MPC fits in what is called the process automation hierarchy. Okay, so the idea behind MPC. So I'm going to use an example of Formula One car, and the emphasis is not necessarily on the Formula One car, but then just driving in general, right? And I'm sure a lot of us drive or know how cars work, right? So the goal here is to get the shortest lap time. And this is not my example. I saw this example somewhere and it made perfect sense. So that's why I'm using it. So basically, you have your racetrack, and the goal is to get around the tracks as quickly as possible, right? And I'm sure if you have to guess, for paths that are straight, you want to move as quickly as possible. And when you're negotiating curves, you want to be careful that you don't go off the track, because if you go off the track, then you would violate the bounds / the limits of the track. And that's an example of a constraint. So if you go outside, that means that you violated constraints and you have to pay for that, right? So the goal is to get this done as quickly as possible without getting out. So this is a classic optimization problem. We write up the model of the racetrack. We give it the car model because we have a maximum speed limit that the car can go. We have to factor in things like overheating, because you can only work your car so much, right? So we do this, and then this is what the optimizer gives us. This is the way we can get around the track as quickly as possible. The darker the color, the faster the speed. So as I mentioned, if the track is straight, then you want to go as quickly as possible. However, if you have to negotiate a curve, then you want to slow down, right? So we have this, and we are happy that we're able to get a good solution. Then we start driving, right? You start driving, and then there's a car ahead. You're not allowed to knock that car out of your path, right? So what that means is that you have to decide again, okay, initially you hadn't factored in the fact that there was going to be a car in your path, right? But now there's a car in your path. How do you do the best under the circumstances to ensure that you don't end up spending too much time, right? So meaning that you have to go back and do the computation again, because things have changed, right? And a lot more things could have changed. Say at the time that you were at the start point, say here, it wasn't raining, right? Then when you got here, it started raining. You can't go at the same speed again, because if you had to go at the same speed, chances are that you're going to skid off the racetrack, and that will be a violation, right? So there's a need to be coming back to do the computation. So this step of having to come back and do the computation we call feedback, right? So what you realize is that you have to be coming back to do this computation depending on how things are changing, right? So and this thing of having to go back and do the recomputation is what we call feedback, right? So this in principle is how MPC works. So you're using optimization to calculate the best path. However, you take a step forward and then things change. You have to come back and recalculate, right? In that fashion. So to summarize, our goal was to minimize the lap time. Some of the constraints are that you have to avoid hitting other cars. You have to stay on the track. You have to make sure that you don't skid. And then, of course, there's only so much your engine can do, so your acceleration is limited, right? And things like that are likely to change as some of these things. So road conditions, upcoming corners, ability of your car, etc. Right. So this problem of having to get around the racetrack as quickly as possible having to redo computations is what NPC is trying to do for a plant, right? So to take it home, I'll use the example of a distillation process. So for a distillation process, you have the feed coming in and you have your product streams going out. An example of an input slash a lever to control the process would be your boil-up ratio. So let's say something happens to your feed, which is the disturbance. In this case, would be would take the place of, say, rain happening on the racetrack, as you hadn't seen before, right? So maybe the feed temperature changes or the feed coming in has some amount of impurity. Although you had designed the process for a fixed set of properties, now that things are changing, if you want to do the best, then there's the need for you to go back and recompute, right? So in that case, you may decide to change something here to increase the flow of liquid going back to the column, or to change something here so that the vapor going to the column would counteract the effect of your feed stream coming in. And this is very real. Like, this happens in real life, because whilst for those in final year, you're doing your plan design, you pick a set of numbers and then you stay with it. But in real life, it doesn't stay like that. For instance, you designed your distillation column during Harmattan, when maybe the day that you picked was very cold, and rainy season comes and it's really hot outside. Chances are that there'll be heat leakage into your column, and you wouldn't be able to operate as normal. So something has to change, right? And you want to do this systematically. NPC helps you do things like this, right? So this is sort of like a diagrammatic representation of what is going on. So you constantly have to be measuring. So you measure, you send it to your NPC, it does a comparison, sees what's different, and then it makes an adjustment, sends it back to the plant, and then you keep on doing it. Now, as to what it looks like, this is a representation. So the time point that you are, we call it K, right? And we are just looking at steps. We're just looking at time steps, right? And as some of you may be aware, instruments don't measure process variables continuously. They do it at intervals, right? So basically what you want to do is that you want to be able to do things with each interval of measurement, right? So that is why we have the time steps here. What the NPC tries to do is this. As I mentioned before, you want to be able to make a prediction into the future. However, you can't do it infinitely. It has to be finite. You have to define a range into the future to which you can make this prediction. We call this window of time the prediction horizon, right? Now, you have your set point that you want to reach. Obviously, you don't want to just, move there as quickly as possible, because if you're aggressive with your movements, chances are that you would make the process unstable. So you want to approach that set point gradually. So the dots here kind of are the measurements. So they tell us where the process is in time. And then this line here shows us the set point. So obviously at time K, at the present time, we aren't where we are, right? So we want to be able to make some prediction, and we want to be able to compute what our inputs will be in such a way that we're able to reach our set point in a finite time. So the time window for which you compute your inputs to get to this point is what we call the control horizon. Now you can see that that is different from your prediction horizon, because you are predicting all the way to this point here. However, the control is just up to you, because the control gets you to that set point, and then it doesn't change anymore, as is shown here, right? As I go along, I think these things will become much more clearer, right? So I'm hoping by now you will have a sense of what is going on. Can I get another poll, And if there are questions, feel free to ask, because I don't want to pile on too much. I want to make sure that you are with me. So checking maybe a thumbs up or something.
Okay. Please, if you have any question, drop it in the chat. Please, you can continue.
Okay. Good. So moving on to the formulation now. This may seem like a nose type, but let's see. So when you're trying to formulate an MPC, what do you need? By now, I think we may have gotten a sense of what that is. So in the example of the racetrack, I mentioned that there was a goal. Right? So I'll go back again for you to see. I mentioned here that there was a goal, and I intentionally put in brackets objective because that's a term we use. That's a technical term, objective, right? So you first off need your goal, and this is not a vague definition. It has to be exact, as I mentioned. You have to be specific, right? One of them is to get to your set point the best way possible, and I say the best way possible because the best way possible is not necessarily the fastest, because maybe if you approach your set point very fast, you're going to destabilize your process, right? So you want to get there the best way possible, and of course you have to define it exactly using math equations. The next obviously is your model, as I've been hinting at the whole time, sorry. So let me see, let me go back again. Where did I show that? So you see you need your model, and you may have guessed I mentioned things like constraint because I mentioned that IPC is good at handling constraints. So these are the main things that you need in your MPC. Obviously, you need your reference. Your reference in this case is the set point that I mentioned. So as I put here also, right? Then what the MPC does is to compute your inputs. So your inputs, and another term for inputs is manipulated variable. And then your output. So output are what you measure, your measurements. So this and this. And then you can also, output are also called control variables, right? So these are the terminologies that are used with MPC. So you have your MVs, you have your CVs, right? So the question is, okay, what does my objective look like? It could be a number of things. It could be, the sum of squared errors. It could be absolute errors. It could be economic. For instance, you want to maximize the oil that you're producing from your refinery. You could actually set it up as your objective. Okay, I want you to maximize the profits from the process. You could do that. But one thing to know is that the more complex the definition is, the more difficult it would be for you to solve the problem, because at the end of the day, you're solving a mathematics problem and complexity matters, right? Then of course, your dynamic model, and that also comes in different flavors. It could be linear, it could be non-linear, it could be, here I put single slash multi variable, but most often than not, you're working with a multi-variable system. And the number of variables that you have also impacts how well you're able to do. So in terms of linear versus linear, a linear model is one where your term, so in this case, let's say your x here is your variable, is being multiplied by a constant term. If you have the case where, let's say, the variable is multiplying another variable, then that's a nonlinearity, and that's another level of complexity, right? And depending on what you end up with, you have to handle things differently. The thing is that linear models are the best because they are quite simple to solve. They solve very quickly. And the way that MPC got far is that linear models were leveraged, right? So linear models look like something like this. So this equation here, the technical term is sort of like state space representation, right? So this X is not necessarily a single variable. It could be a vector of variables, but just for representation, we just write an X, right? So this is sort of like the mathematical form. And this thing here is what we call an optimization problem. So of course you have your objective function, and then you have a set of equations that must all be satisfied, right? So what MPC does is solve a large number of equations at the same time. I mean, there are complexities, but for now, let's just think of it as a simultaneous set of equations being solved, right? And in terms of constraints, this also comes in flavors and forms. So for instance, your inputs, right? So earlier on, I mentioned that your input could be the flow of the feed going into your CSTR, right? Now, your flow can't just take on any value. If your tank is the size of, say, a 1 liter bottle, obviously your flow can only be so much before your system overflows and causes issues. So what that means is that there's going to be a constraint on the maximum flow, right? So that's what we call an upper limit, right? There could also be a minimum limit or a lower bound to ensure that your thing doesn't run dry. So for instance, if you have fermentation tanks, you can't send it too much flow, you can't send it too little flow. So these limits we refer to as constraints. Constraints could also be related to environmental variables. So as I mentioned earlier, maybe you are not allowed to release certain gaseous constituents, right? And all of these, so far as you can write them, you can add them. But the thing to keep at the back of your mind that whilst you're at liberty to put in all sorts of equations, the more you put in, the more your problems get complex, right? So you have to make decisions as to what to put in, right? And I'm sure by now you're getting a sense of some of the challenges that you're likely to face and why MPC, even though it's exciting, is not necessarily easy because there are all these things that you have to kind of factor in as you're building an MPC. So I guess that's a nice segue to the challenges when it comes to implementation of your MPC, right? So I put here challenges, opportunities. I say that because MPCs have been around since the 1970s, and we are still working with MPCs. We are still trying to uncover stuff, right? So the last part of my PhD, I actually did a project which had to do with MPCs, right? So even after, 40 years, we are still researching into MPCs. And the reason why we are still doing that is because there are challenges to be addressed. So in fact, truly, the answer to this question here is a yes. And challenges are opportunities. So what are some of these challenges? The first is implementation. So as I was trying to hint at earlier, if you are defining your model using, say, a nonlinear equation, right? So during the modeling process, you wanted to be exact. You wanted to make sure that your model predicts exactly as your process. So you are pushing the bounds. You are using all sorts of functions. You realize that if you use a sign somewhere, it will give you a better prediction. Know that when you're going to use an MPC, you'd have to pay back because those functions are much more difficult to compute, right? And we can see why. If I give you, say, 2 plus 2, you can do that straight off. But then if I tell you to find sine 39, it will take a bit of time. And the computer also struggles to get this right. So these are some of the things that you have to think about, challenges with respect to implementation, right? And maybe you get excited. You hear that, okay, MPC can solve all your problems. And then you go and tell your boss at Thermal Oil Refinery, hey, you know what? I did a bit of modeling at school. For my final year project, I've written up the model. Let's go solve. That model is probably not going to help you because it is probably too complex. There are things in there that are just way too difficult to handle. The other challenge has got to do with stability, right? So whilst we are trying to do the best we can, there's no guarantee that the process will necessarily be stable, right? So this is where the art there's a bit of art. So I'll go back just to kind of illustrate that. So here we have our objective function. This P here is what is called a tuning parameter, right? You can't know offhand. You have to kind of play around to kind of, for lack of a better word, help you achieve your goal, right? So, and in terms of stability, what we mean is that you're trying to approach your set point. You get excited and you're like, I want to get to the set point as quickly as possible. So instead of having to take the gradual path, you get aggressive. So maybe moving from this point here, you come all the way here, then you go all the way here, you hit your set point. But are you guaranteed that your process will stay at this operating point? Not necessarily. So that's what we mean by the challenge in terms of stability. And these are all opportunities for studies, right? So you have people who...
Hello, Q.
Yes.
Isn't there also an opportunity cost taking forever to reach the set point? Like assuming the temperature is low, so I don't know, I'm producing some, I don't know, undesired product. Taking forever to reach the set point, isn't that also some form of cost that I have to wrestle with?
Yes. Of course, whilst you want to do things gradually, you don't want to be sluggish also, right? And I didn't show the form, but then okay, maybe this I can use this to explain. So early on I mentioned that you want to get to your set point, right? So in that case, that is sort of like a process variable you're going to get to. But you realize that in the equation here, I have the U. So U is supposed to be my input, right? So meaning that I take my inputs into consideration. And the most classical MPCs, what they do is that they actually put a weight on the change that you can make to your input, right? So your temperature, you can actually constrain it, right? So from what you're saying, depending on your process, maybe your process is such that you need to be sharp, then maybe you want to put less emphasis on that input, right? You want to give it that room to fly around. And if there's an input where things are a little bit more sensitive, then you want to be careful how you move it, right? So I don't know, does that help? Does that help answer your
No, it
question?
helps. It helps a lot, yeah.
Yeah. The other one is robustness, right? So I mentioned that, okay, there's a lot of uncertainties in the market. I'll go back again just to kind of take the point home. So a lot of uncertainties at the top level. And the thing is that once you're trying to do this optimization, you don't take every single thing into consideration. It's sort of like approximation, because as I mentioned earlier, the bigger the problem, the much more difficult it is. So you have to make some assumptions somewhere, right? So there's a chance that, in making an assumption, you come up with an operating point that is not necessarily within the operating range for the MPC to implement, right? So there's uncertainty, but then there's no guarantee that you'll be able to address that. And this is also another field of study. So there are people who study and say, okay, we want to come up with the most robust control possible. So they test all sorts of uncertainty. So these are all like huge fields, right? And lastly, there's feasibility. So feasibility has got to do with the fact that, okay, be able to solve your problem and get a solution, right? So if I can attempt to explain this, we all did calculus, and we've dealt with quadratic functions, right? So we've dealt with what is called the gradient. We compute what is called the gradient, and we compute what is called the minimum or the maximum. And yeah, we've been taught how to even spot it right away, right? Depending on the sign of the coefficient of, say, the square term, you're able to tell whether the function is going to be a minimum, a maximum, right? So optimization actually takes these things into consideration. But as I mentioned earlier, there are things like constraints. So constraints pretty much just say that maybe your operation is such that you only have access to maybe half the quadratic function, right? So let's say you have your process is in the shape of a U, and then you have constraints. So constraint says that, hey, maybe you're unable to operate your process below 50 degrees Celsius. What that means is that your operating window is just half the U, right? And there are a bunch of all these constraints. You put them all together, and then it's like you're trying to solve, you're not able to solve it, right? So that's another challenge, and people actually research all these things. So the last part of my research, the thing I looked at had got to do with implementation, because my process is really huge. It's very nonlinear. And what this means is that whilst I may be able to solve it, it's going to take so much time, right? And why is time important? So I mentioned here, right, at this point that, okay, there are time steps. You make measurements at periodic intervals. What this means is that there's a limit on the time available for you to do your computations, right?
Hello.
Hello, yep.
Yeah, I think someone has a question.
Okay.
It's in the chat.
Me,
From Kran Yabuamak.
okay,
He
let me
wants to
see.
know how machine learning can be integrated with MPC.
Oh, that's a good
Uh,
question. That is something I'm actually working on. So there are a number of ways. So I've seen people actually try to solve, let me go back to that formulation. Solve this thing here using machine learning. So what is machine learning? Machine learning is, lack of a better word, I'll say a model, right? So maybe we there's an input output, right? So let's say input and there's an output, right? Given an input, give me the output. What I've seen people do is that they kind of solve this thing. The right time is offline. So not when the process is in operation, but they have the model and then they have so much time available, so they're able to solve and get a representation. So they can populate it in a table, right? So they know that given this input, I'm able to compute this output. And what they do is that they use a machine learning to kind of get the representation, so that given an input, they are able to quickly compute the output, right? So that is one way of using machine learning. Another approach is to say that the process model I have is too big. It's too hard to compute, it takes too long. So I'm going to use machine learning to get a model of my process, right? It may not be exact, but then it may have good good prediction, and the range is such that I'm able to use it, and it computes way faster, because as I mentioned, you have a time window for which you have to do your computations, right? So this machine learning model computes faster, so I'm going to replace my so-called first principles model with the machine learning model. That is what I am actually looking at in my position as a research assistant. I hope that answers your question.
yes, I think so.
Yeah, so yes, so I mean, I'm actually done. So yeah, keep the questions coming in.
Okay.
We don't have any other question yet. So I think after the presentation, we'll ask our questions then.
I
We'll take
see.
it from there.
Well, I'm actually done
Done.
because I wanted this to, I mean, it is quite broad, and I didn't want to go too deep. So I was just hoping to just, touch on the surface. You guys come up to the topic, because my impression is that beyond that, there'll be an opportunity to, dive in deeper in other forms, right? So there may be some materials, there may be some videos that may be posted later on. So I didn't.
Thanks. You actually
So,
have a question here.
yes,
Uh,
yes.
Because you use GPros at the time, from what I see from your profile,
Yes.
right? So I want to ask
Yes.
a question on initialization.
Yes.
So please, for the other people, initialization is when I want to solve, let's say, Pen Robinson equation. But I first solve an ideal equation to get some certain points which can be used to solve the Pen Robinson equation. So I don't know, does initialization techniques help with some of these complexities? Well, let's say I want to solve a nonlinear thing, but I first solve the linear one, get some starting points to approximate the nonlinear problem.
Yes, that actually is a very good approach. And So let me see which of these this will fit under. I think I probably even jumped because I mentioned time. Oh yes, the implementation, yes. So as I mentioned, one of the things I had to deal with for my MPC problem was on the implementation side. Now for implementation, there are so many things that you can do. Some people kind of replace the difficult problem with a simpler one. There are ways to kind of approximate, right? But for me, what I did was on the initialization end. So the way I did that was that so I'll go back to this thing here. So you see that all these points, we keep on making computations, right? So when you get to, let's say, this point here, you're going to make a future prediction. When you get to this point here, you're going to make a future prediction. So in my work, what I did was that I'm like, since I'm making predictions into the future, why not pick this prediction to kind of initialize the problem, right? Rather than having to start from scratch. Because I'm having to start things from scratch, whilst you may be able to solve it can be a lot of work. So what I did was to kind of take the solution or the prediction from a previous step. So in this case, let's say you're working in real time, right? So this is the current step. I take the solution I got from here to kind of initialize this, and that helped me save a bit of time, right? So initialization is big. Like there are books written on just initialization, right? And when you talk about initialization, they are on so many levels. I just want to say so many levels because if I'm to get into the details, you're not even here today. Yes, Derek. I see that Derek has a question.
No, thanks. Yeah. Thanks. When it comes to initialization, very important. I try to teach the students some small initialization. They don't always get me, but yeah.
Oh,
as I become better one day.
Okay, so I just wanted to add something with the initialization. So I think since we're looking at dynamic optimization, that is like the model predictive control, because at the future times things will change. So initialization can also change. So after every step, after every time step, probably your model should also suggest a new value to reinitialize it. So that comes with reinitialization. So I think that also works with MPC. Yeah, I just wanted to add that.
Okay, good. Yeah, it's true. So one of the things you want to do is, I mean, you do your best to leverage the information at your disposal, right? But the thing is that if there's a huge change, then yeah, you're in trouble because in my case, the uncertainties I was looking at were not too big. So my model is not changing too much. So having to use the solution from a previous step does help. I see Baggy has a question. Yes, Baggy's nice.
By the way, I think so. Baggy is also I think he's Dr. Baggy. He has a lot of expertise in modeling. Please, let's hear you.
Okay, so thank you, Dr. Kwashi, for the nice presentation. My question here is, well, I have two questions. One is about the cases where your state variables are not observable. So what are your recommendations on basically handling some of these non-observable states? And my second question has to do with people who are starting out, who are interested in exploring ways of implementing MPC. For instance, some of the final year students, for instance, may be interested in maybe implementing it. What are the tools out there that they could use in terms of even practical implementations where they actually see it in action, even if it is just a PID beyond what we see in Simulink? What are some of the tools that they can actually use where they interface maybe the hardware with the software parts to actually see some of these implementations? Thank you.
Yeah, no problem. I think I got your second question. So myself, so when you talk about practical implementation, there are levels to it. So you can actually work with the hardware, as you mentioned, or you can just have, let's say, a demonstration, right? A model. And I think that's still a good experience. Myself, I never really had the hardware implementation, but then it's still useful experience because when you in the field of work, there are people who is to do with hardware and yours is to do but of course you benefit if you know. So in terms of hardware, I know that there are Arduino boards.
Okay.
I've seen undergrads here use that. So the Arduino boards that you can configure, you can write whole things, simple software, and then install. And I can only guess the platform to do that because I haven't done it myself. So I'm guessing maybe C++ and stuff like that. I don't think the likes of MATLAB work. It may work or not. I think one thing that may also work is LabVIEW, right? But I mean, you are better off learning C++ because there's an easier access to that compared to things like LabVIEW, which it's I think is not an open source tool. So if you can ask your, oh yeah, so that's on one end, and if you want to learn the software end of things, there are a bunch of materials out there, but then one of the places where I think you can check for good material is AP Monitor. So just Google AP Monitor out. Let me see if I can put that in the chat. AP Monitor. So the prof there is called John Hendengren. He's helped me a lot. Like I go to his page and then I learn a ton of stuff. He has open source tools. He has a bunch of videos. He takes his time to explain. So he's going to take the thing from the simplest case and then try to build his way up. So that's a resource I would recommend. So sorry. So your first question, I think I missed that. If you can ask your first question again, Baggy.
So my first question is about cases where some of your variables are not state variables are not observable. So
Yes,
how then do you handle some of these situations?
So there are ways of there may be ways of doing it. I'm trying to think. I mean, that's where the realm of filters come in, right? So basically you build what is a filter / estimator. So as I mentioned, I was trying to draw, let me see, parallels. I was trying to draw parallels here that you have your outputs, right? And your outputs are things you're able to measure. And I mentioned the case of CSTR where you're able to measure just a subset of the concentrations. You don't measure everything, right? So I think what Baggy is saying is that for you to do a good job, you sort of have to know what's going on in the inside. So observability has got to do with the fact that the information as you're getting is not fully reflective of the system, right? And what could potentially happen is that if you just work with that limited view of the system, you may compute an input which may end up being detrimental to the process, right? So this way of going about it is to use what is called filters, and that's also another huge field, right? So you have your things like the Kalman filter. That's like, I wouldn't say the simplest. I think Remember guys, the filter is the simplest, right? You have things like moving horizon estimators. I don't want to get into the details because I feel like while some people are way ahead, some people are now coming up, right? So basically there are techniques to deal with this observability issue, right? So depending on the nature of the process, you have to see what works best for you. But it's something that can be added to the challenges that you have to deal with. So Baggy, I don't know if that answers your question.
Yes, that answers my question. Thank you very much. I think there is someone in the chat who wants to know what kind of models and algorithms that are used. I think, yeah. So that's what I mean now.
Oh, so I've these days there are a bunch of so in terms of the model types, these days people try to use every single type of thing, right? So you have linear, and even linear, there are different variants. So you have like what I showed you is called a state space. You have auto regression, you have step response, you have first order hold. So there are a bunch of techniques out there. And the interesting thing is that these are not necessarily theoretical where maybe you just do it in school. Some vendors out there actually do their MPC formulations to use these type of model forms, right? Of course, you have to be careful about the flexibility. You can't just go like, oh, I see that this package allows linear dynamic models. I'm just going to make sure that I put everything in. Yeah, likely to run into issues. The rule of thumb is that you start from the simplest, and you start with the simplest model that you can get, and you don't need to go beyond that. If let's say the simple model does a good job, that's it. Right? I don't know if that answer is sufficient to the person asking the question. If there's something else you want me to clarify, I'm happy to.
Okay, Humo. I think that's the name that I'm much more used to. If I'm to ask a question,
yes,
is there like a GUI version of the software? So yeah, there's the code-like version where you write all these equations. I don't know. Is there a GUI version of a model predictive control software where the person just tick some stuff?
Oh, I think
so they go and choose them.
I think there are packages in either MATLAB or Simulink.
Okay.
Yes.
Simulink.
Okay. Yeah.
Simulink works.
Okay, so they have GUI packages.
So the thing is that what I know is that I kind of work with some of these huge things. So I don't use it, but I know that it is there. Yeah. Thanks for that, Bergie. Yeah. But the thing is, I mean, it's good stuff from that end, but you want to
at some point you have to do the real thing.
Exactly. And what I've even found is this. Even things like this are scratching the surface, right? Sometimes you have to go even deeper. You want to check, the low-level mathematical operations happening on the computer. And that can even inform whether you even want to work with Windows or maybe things like Linux, right? Because Linux has a bunch of these things coming up with it. And if you want to do a really, really good job at the industrial level, then you have to be prepared to go deeper, right? And you'll be amazed, there are chemical engineers out there who are doing these crazy things. So I'll give you guys an insider information. So I'll mention the name, but I was talking to someone from the industry and I asked, okay, you guys, your package is really, really good. I saw a presentation that you gave a long time ago. The core of that MPC technology, how has it changed since that time? And the person was like, it hasn't really changed. It still works as good. Our customers are happy. We don't have to change it, right? This is just to indicate the level of maturity of MPC. Nonetheless, it doesn't indicate that there aren't things out there to do, right? But I guess all of this makes it exciting.
Okay, so Q, the reason why I said that is that sometimes when people are very new, you might want the learning curve to be a bit short.
True.
So GUI is never for an expert. But sometimes when someone is going to shoot for the first time, you might want the learning curve to be a bit short. Then later, maybe they kind of expand their horizon.
What I think is that sometimes when the thing is overly simple, you
miss out. Okay.
You may be reluctant to get deeper to kind of know that. So the thing is, you want to know the fundamentals as quick as possible. Because sometimes when things are just on the surface, you take things for granted and then you miss things. Yes, I see that Dr. Dadibo has a question. Oof.
I think someone had a question.
Yeah, Dr. Dadibo has his hands raised. I'm not able to, let me get out of this. Let me stop sharing.
Dr. Dadibo, please, you can ask your question. Please, admin, is there a way to unmute everyone so that when people have a question, they can ask?
trying to set this up. I think, let me see if I can unmute him.
Yes, please. The person can unmute.
Okay.
Okay. Well, thanks. I was just gonna, I guess, answer some of the, the questions. I actually taught model predictive control and optimization for several years at University of Buffalo. And it shouldn't, if you're a student, don't let it confuse you with the math involved, because we actually have hired students right out of school. We teach them for a week on implementing process control applications in the plant. I was working in an industrial gases company, so we were actually doing practical applications in the plant. So it shouldn't once you understand the basics on how it works, how you actually use the software. Some of them you could use what we called, I think the question mentioned impulse, generating finite impulse responses, where you pulse the first, you just make changes, put a shock to a plant, you move a flow control set points or move a valve just to see what it does to the process. It helps you to capture if there's a time delay in the system, how it responds and flows to, you see some type of first order response or whatever the model is. And you use those points in generating your model. So you don't have to physically be calculating things other than just doing it and collecting the data. And then you can use it to generate models. And from there, you can use it to do simulations. And then you put it in AspenTech actually has a software where it can actually convert the model from one form to another if you want. But that's all you need to know, and then it would do it. You have to then provide the inputs required for optimization, what your control variables are, which ones are input variables they use, and which ones are the control variables. And once you have that and you give it an objective function, what is more important? If there's a purity constraint, as an example, you can't go over particular point. Like we had a plant where we were making carbon monoxide, but there is a carbon monoxide distillation column, and the last control distillation column, you have carbon monoxide in the overhead and methane in the bottoms. But having, I think, points, I can't remember, but a few, maybe 5 ppm or so was the level. You cannot go beyond that. And so you can't even send the product to the customer. You have to just recycle it or just flare it. That's how bad it was. So things like that, you have to know these limits. And so the controller would do all that for you. So don't let the math scare you. It's once you're in industry, it becomes something that you apply. But if you're doing graduate work, then you just have to understand a little bit of the math on how to derive the objective function and the calculation on how you actually calculate some of the charts it was showing. So you shouldn't let it bother you too much. But it is actually a good area if you're into chemical engineering and you're doing advanced process control and optimization. Up until the last 2-3 years, it was a very, very good area to get a job. So I just wanted to add that.
Thanks for that comprehensive answer. Some of us we don't have the field experience, so it's always on a privilege to have Dr. Dadibo share his insights, because he's been there, he's done it not just once, not just twice. And if you're not aware, Dr. Dadibo has patent to some of these things. So yeah.
No, thank you. Well, guys, any more questions? We don't want the old guys to take over all the questions. So I just want to make an announcement. I feel like Q kind of hinted. So one of the reasons why this platform was created was also for some form of knowledge transfer. Because of the kind of country that we have, we don't always have the money, so you cannot always, hire the top talent to bring down. But the hope was always that people who started from here and they've discovered something new will help us develop local curriculum here. So Q has been nice enough to say he'll help us do stuff like that, gather material and send some videos explaining model predictive control to us. So yeah, we'll put together a team if you want to be part. I think whoever should be part should be either a final year or a TA. Yeah, let me know so that when we start working with Q on developing some content on model predictive control, you can join in. Oh, thanks once again, QMO, for such a masterful lecture. I really enjoyed it. Guys, any other question?
Okay, so this is a question from Joshua. He wants to know if he wants to learn MPC, how and where do we start? Like if you want to learn MPC, how and where do we start? And are there any websites where we can learn about and practice the use of MPC?
Yes, so I think that there are quite a few out there. So I think I'll just put in the chat for you for everyone. So in terms of so one of the resources that helped me was this professor called John Hendergren. So he's the creator of AP Monitor. So he actually has content on even some of the things that Dr. Baggy was talking about. So, and the thing I mentioned along the lines of that Arduino thing. But then he also has stuff that you need Python for. So he has content on Python, on MATLAB. I mentioned Python because it's open source. You don't have to worry about having access, and you start from the basics. So for him, and for a lot of the guys in process control, you start with CSTR, and CSTR is quite flexible because you can actually start with very simple models, and you can go on to make it much more complex. And then as you get comfortable, you move to large scale systems. So as Dr. Dadibo mentioned, you don't necessarily have to get everything. You just need something small to start. And as you move along, you learn more and more. But the resource that comes to head and I know can be beneficial is the AP Monitor Creator. Let me just put it here. Yeah, I hope that helped.
Yes, please. And I think there's a question in the chat from Edward.
Okay. And even just to follow up on that, so actually MATLAB has resources also because MPC has been out for some time. The fundamentals are no longer hidden. So you go to the help page. You can even just help MPC get so much, and even on the website you put in MPC, you have so much. There are automatic implementations of MPC. So some of the things that Dr. Dadibo was talking about. So you have the model in one form. You can ask MATLAB to change it into another form so that you can use it for your MPC implementation. But then if you want to, get down, do everything, then of course you can also write it yourself or move to things like Python. Yes, Derek.
Yes, thank you, Dr. Kwashi, for this insightful presentation. I really meant a lot, and thank you for the high level presentation on MPC. So what I just wanted to add two things. I think they've been touched already. I just want to emphasize on it. So with the final years, I think that they could start playing around with like the Simulink software. Like if you really, I think if you really want to understand such things, maybe going down to the modeling and the optimization and those granular stuff might not be helpful, but just take the CSTR or take a very simple MPC model, go to Simulink. I think you guys might have access to it. Just take some time, play along with it, change some variables, look at the way it changes with time, try to change some coefficients. I think that would help you understand the core. And secondly, on the other part of the modeling, let me say, the low level part. I'll say it's not far away. It's just the normal CPC models, the normal heat transfer models, H is equal to Q is equal to MH or something. Those simultaneous, like the normal ones you write when you're about to answer question 1A or question 2B. Those are the things you just add them. But having more information about the particular system would guide you to set the constraints, maybe the goal. And sometimes the goal is not only to minimize or maximize. It could be a particular production rate, because maybe the global optimization, as Dr. Kwashi mentioned, that there are top-down analysis, maybe from the global side, based on the demand, you're supposed to produce 1,000 gallons per day. So maybe this extractor or this centrifuge unit should have a throughput of 500 kilogram per minute or something like that. So in that case, that would be your objective function. So objective functions are not always the minimizing and also the maximizing. So I think playing around with this, reading around in your leisure time, at least you have stuff to do, just read around. And when you're done with school, when you get to graduate school, that's where you have hands-on experience and you have industrial experience to go deeper. Yeah. So that's it. Thank you so much, Dr. Kwashi and Dr. Dadebo and Dr. Bagi, Dr. Boensu. Yeah.
Okay. So what I want to say is that we do teach optimization as an elective. It's just that for some reason, I don't know, Q is here, he will testify. I used to be a cool TA. Somehow I'm not a cool lecturer. Like I used to be one of the coolest TAs that somehow when I became a lecturer, it has changed a bit. We do teach optimization, but some of the students are avoided that. And the math is not even that hard. The math in optimization usually for me is numerical in nature and stuff like that. So so those of you, at least you could have avoided the course, but yeah, if you still want to have a foot in optimization, a foothold in optimization, I don't know. You can take the material and read later. If it was the exams you're scared of, you don't have to be again, because now you take the material and read at your own leisure time. And there are also a lot of short stuff on optimization. I think that's what I would say.
Okay.
So
Thank you
I'll
very
just
much.
Gabriel, go
Please,
ahead.
you can go ahead.
So I was just thinking that in terms of the optimization, because I believe optimization is something that is necessary for every chemical engineer, right? So why not build the optimization aspect, which is a subset of numerical methods, as part of the numerical methods course that they do, such that they have at least a taste of it, and if they want to go into more details, they would go a little bit more into the optimization aspects.
No, I'll try to speak to the colleagues teaching America that if they can do basic. So I think someone asked, what softwares that you can use for optimization? So the most basic one, which you not learn too much, but it will do a lot of optimization, will be what you call Excel solver. So now we'll try and talk to some of the colleagues doing teaching numerical methods to see if they can do some, I don't know, basic optimization in so basic program formulation, not so much into your solution techniques, your branch and bound and stuff, but
yeah, don't feel too intimidated, because we all had to, we all knew nothing at the point, but just by doing incremental work, we are where we are. And up to now, for me, I still feel like I have a lot to learn. Because I go to places and I see people present stuff, I'm like, wow, okay. Right. So don't feel intimidated at all.
Okay. I think there's a last question in the chat. Edward is asking, please, are there some soft skills in programming to learn to help our journey in optimization, or MPC is it for further education?
So if you can come again, I didn't get the first part of the question.
Are there some soft skills in programming to learn to help our journey in optimization, or MPC easy for further education?
So what I find is this. See, when people ask me if I know programming, I struggle to answer. I know how to use all these softwares. I can write a program, but I'm not sure I would say that I know programming. Of course, it comes in handy, because if you want to implement the hardcore stuff. You have to know things like information control, how to, pass information. It comes in handy if you know those things. But I would say that they're not a requirement. You don't necessarily have to know all these things. You can start with, crap, because so far as it works, you're good, right? You're good. Over time, you get to see, oh, this is how I do things efficiently. If you're fortunate and you started with programming, that's also fine. But I wouldn't say it's a prerequisite to get into MPC process control. No, we just have to, show up and then do what is there. And there are sample codes. So for me, how I learn a bunch of these things is I start with a sample code where I have some fundamental understanding. Then I start complicating things. Okay, I introduce one level of complexity. I try it. I do it. It may seem like slow pace, but it's very, very powerful. There are complex problems that, I face, and I'm like, let's go back to basics. Let's strip it down. Okay, what is the simplest thing I can start with? Okay, now let's add something, and it works like magic, right? So don't let your mind travel far or have to know all these things. Just find something simple, start with, and gradually complicate it. And before as the saying goes, the journey of 1,000 miles starts with one step, right? Yeah, I hope that helps.
Yes, please. Is there any other question? I don't think there is. Presentation, Mr. Akwasi.
It's my pleasure. I hope everyone was able to pick something,
So please, before we head, I want to say one more thing. So we are building this thing slowly. So I think there was one day who I don't know. I think he's also very insightful. So this thing of people presenting, I think sometimes in Ghana we make it too scary. Like everybody should be able to present on something. But the bigger point I always make is if you feel like you have some skill to offer, let us know. Whether it's mentorship, whether it's let us know. We'll put together a seminar for you. And I want to thank all the students for coming. So Q, Ghana's not like Canada. The internet situation is a little more horrible. I remember when we were students, even when the internet is stable, we always don't have the money to buy it and stay up. So I'm really impressed with the level of attendance. Since tomorrow being, I don't know, Easter exam around the corner. Guys, thanks for showing up and granting us the audience. So, and thanks for all the experts and the senior chemical engineers that showed up to support. Please, if you want to, I don't know, work with us as the Modern Club, please reach out via LinkedIn, via our LinkedIn page, or you can reach out to my personal LinkedIn account to No, thanks a lot, Q. Yeah, you can take over.
I just wanted to thank everyone for coming out. So I was thinking, okay, 7 o'clock the day before Easter, how many people will show up? Right. So I'm really impressed that you all came out and you are all hungry. And this is what it takes. I mean, it just takes hunger, right? And I'm not the only one. I have friends, and it's good to, encourage you. And I made some really, really good friends back home in school, and we are still in touch now, and they're all doing really, really well, right? And we all started from the same point, not knowing much. But then now you look at them like, and we had the likes of Jude, encouraging us, cheering us on, and he's still doing it till date, right? So don't feel like, oh, I'm behind. I don't feel pressured at all. One step at a time, And once you keep at it, before you know it, you're also telling someone, hey, you can make it. Thanks for coming.
Okay. So today's webinar has highlighted the importance of MPC in modern process engineering. We've learned how MPC optimizes process performance and efficiency. So that's like the main takeaway. Thank you very much, Dr. Kwashi. And to our audience, thank you all for your participation.
Thank you. Happy Easter, guys.
All right, thank you. So I think we can end here. Thank you all for joining and have a good night.